So hi everyone. So previously we talked about CEP, which is called a extreme precision design. So in this CEP design, what we're doing is we want to make sure at certain theta values, we want to output certain S values. Okay, so that's our design objective. You want to make sure your S theta reaches certain position when you're at some given theta values. So in that case, we don't care about velocity, acceleration, or jerk. So that's why the design is actually relatively easy. But then here, we're going to have to deal with CPM, critical path motion. For CPM, that means, okay, so it's no longer for theta values only. We want to make sure at certain time points t, your displacement, your velocity, let's name it as vt. Again, this velocity is not v diagram, is actually this is the actual velocity. Your acceleration, again, that's actual acceleration, and jerk, actual jerk. So we want to make sure that at certain time point, your SVAJ should reach certain values. So compare your CPM with CEP, you can see things are more complicated. First, we have 4 design objectives. It's not only S, we have to consider all other 3 variables. And then also, it's no longer in theta domain. We're actually talking about everything in time domain. So that's why you're going to have time, you're going to have theta, and then if you recall, you're going to have x, which is a normalized theta. Okay, so that's why we're going to have 3 different domains. So all your design requirements or the design requirements will be given in time domain. For example, okay, in this period of time, I want a constant velocity of 10 meters per second. That's usually the design requirement you receive from your customers. So that's why everything is in the most convenient or most straightforward domain, which is time domain. The theta domain, which you have your S theta. So this is your actual design, right? So as I mentioned in lecture 18, so when we want to design a cam profile, we actually are trying to design this S theta. And then your X is like an intermediate domain. So in this S domain, you have your polynomial, I from 0 to n, and then you have your S, X, X, I. All right, so this X domain is where you have your polynomial defined. So again, then things become tricky. Your input is in t, you have to go first through t to x, and then go back from x to theta. So in CPM, you're going to see a lot of like domain transformation. So we're going to go over these using one example. All right, let's look at example number 1. Consider there is the following statement of a CPM problem. So it first accelerates from 0 to 10 meters per square second. I think I had a typo there. And then, oh, sorry, it's not a typo. Yep, so it first accelerates from 0 velocity to 10 meters per second. The second one is, let's maintain this constant velocity for 0.5 seconds, and then go back to 0 velocity, and then the follower goes to the stop position. Okay, so whenever you see a time period in your design requirement. You want to convert from t to theta in the first step. So the cycle time is exactly 1 second, and we assume the cam is rotating in constant speed. So that means your theta dot is 2 pi radian over 1 second. So that means your velocity is 2 pi radian per second. All right. So because here we know the data t is 0.5 seconds, then your data theta is theta dot times data t. So that is 2 pi or radian or 180 degree. All right. So that means you have to maintain for constant speed within 180 degree. Okay, so the first step is you always convert your time domain requirements to theta domain. The second part is you need to draw your SAVJ diagram and plot whatever you already know to the system. So your SVAJ, the functions of theta, and then that's your S. Let's name these as your V. That's your A. All right, they're all S, V theta, and A theta. From 0, 0, 0. So first of all, let's look at the first step. The follower accelerates from 0 to 10 meters per second. So we know something about the velocity. So that means your velocity starts from 0 and it goes up to a certain value. So we know that the 10 meters per second, this velocity is in time domain, but then v theta is actually in theta domain. So this amplitude is a question mark. You cannot directly put 10 meters per second there because your v theta is actually has a unit of meter per radian. But then here you have meter per second, so they are in different unit. So you cannot directly put it there. But we know that it has to go to a certain point. Let's name it as v edge for now. All right. So in the second step, we need to maintain these constant speed for 180 degree. So we know that in this region, you're going to have a constant speed, and then the width of these is going to be half pi. That's what we already know. And then the third step is deaccelerate. So the follower goes back to 0 velocity, but then we don't know how fast that should deaccelerate. So we just select a random point, and then we know that is going back to 0 here. And then eventually it returns back to the starting point. Okay. So where's your starting point? Your starting point has a velocity of 0. So let's put a 0 there. Okay, so we know all of these things about velocity. So what we know about the displacement. So your displacement, let's assume it's starting from 0, and then it goes up to some point. So this point we don't know because we don't know how the acceleration look like, right? But we know it's going to end it up in some point, some positive point. And within the second range, because your velocity is constant, then your displacement is going to be a linear function. And then in the third range, we know it's deaccelerating, but then we don't know how fast it's decaying. So it might end it up somewhere on that line. And then in the last one, we know that it goes back to the origin. So that's why in the last time step, it goes back to the 0 point. So then let's look at the acceleration. Again, you have these 4 steps. First, we know your acceleration here is going to be 0 because that's constant speed. And then at the beginning, we don't know the acceleration there, right? There's no hard requirements. And then we know that in this region it's going to be 0. And then in the second region, we don't know how it looks like either. So another question mark. And then in the last one, question mark. So we know very little about acceleration. So before you design your SVAJ diagram, you have to specify your step width. So in this case, we only know the width of the second step. We have no idea about the other steps. So you have to make assumptions. So here in design number 1, we assume that the first segment is 30 degree. So that's 1/6 pi. And then by adding these half pi, so these becomes, oh, I think I had it wrong. So that should be a full pi because it's 180 degree. And then there's also a typo there. That should be a full pi. And then we have 7/6 pi. And then we assume the third segment is another 30 degree. So that gives us like 4/3 pi. And then in the end, there's a full rotation. It goes back to 2 pi. All right. So once this is defined, we can start design things. So again, similar to the CEP design, we want to design this thing section by section. So first of all, let's look at segment number 1. And then let's take a snapshot of the SVAJ in the plot. So your your theta is from 0 to 6 pi. And then we know that it's starting from 0 and is going to end it up somewhere, but we don't know where it is. So this point is actually a question mark. All right. So the second plot is theta. V theta starts from 0. Same 1/6 pi. And then we know that the velocity is initially 0. And then we also know that it's ended up somewhere in a VH, right? Because that's a constant speed we want to achieve. And then in the acceleration, theta, the same angle values. And then we know that we don't know if it's starting from 0 or not. So the first point is a question mark. And then we know that this point is definitely given. So that's 0. All right. So here for the CPM, we're going to use the polynomial method again. So first thing we need to figure out is what's the maximum order of these polynomial. So we need to find out how many boundary conditions are already defined. So I'm going to use a red color. So these boundary is known. These 2 are known. These is known. So in total, you're going to have 4 boundary conditions. So that means your Sx equals to C0 plus C1x C2x squared plus C3x cubic. Because we have 4 boundary conditions, we can only assign 4 unknowns to the polynomial. So your Sx is here. Your Vx is C1 plus 2C2x plus 3C3x squared. Your Ax is, let's put a small x on as a subscript for v and a, so we know that these v and a are functions of x. So that's 2c2 plus 63x. Okay. So in order to solve these unknown coefficients, we need to get the boundary conditions in x domain. But again, as I said, all the boundary conditions are given in time domain. How can we convert it to x domain? So no worries. Let's just first lay out all the domains. You have time domain, you have your theta domain, you have your x domain. So the equation between t and theta is you have theta dot times t equal to theta, right? Because we assume there is a constant velocity of theta dot. And then between theta and x, you can go back to the CEP, and then your x equal to theta minus theta naught over beta. And then your beta is the width of the segment. So in this case, your beta is 6 pi, 1/6 pi. And then theta naught is the starting point, starting theta of your segment. And in this case, your theta naught is directly 0. So that makes your life much easier. So we know that everything is given in time domain. We know that your displacement time equal to 0. That's 0. You know that velocity, that's in time domain. Let's put a small t as the subscript, as vt equals to 0. And then we know, so that's a 2 coefficient. And then we know that vt when t equals to, so this time point is 1/6 pi over 2 pi. So that's actually 1/12 second. So that's the t1 corresponds to this to the ending point. So when t equals to 1/12 second, we know that that's 10 meters per second, right? That's the value we were given in time domain. And then we know that the acceleration t equals to this at the same time point. That should be 0 meters per square second. All right, so everything is given in time domain. How can we convert everything in x domain? So that's the trick we need to play. All right, so first of all, one important thing, you can directly move s values between domains. So that means whenever s you have, so that's why we never put a subscript for s for s, because no matter is st, s theta, or sx, you can directly deliver your s displacement values. Okay, so the second thing is, let's look at the velocity. How to deal with velocity. So that means whatever s is given, you can directly put it in other domains. But then how about velocity? So as we call, your vt time domain velocity is d s dt, right? That's by definition. And then we already know that your vx, your velocity in x domain, is ds dx. Because, as I said, we have the same s in all the domains. So that's why your denominator should always have these s in it. And then how can we convert x to t? So what we're doing is you can apply chain rules, d theta, dt, dt. All right. So we're not making any difference. We just multiply two redundant components to the equation. But then things becomes tricky. So ds dt, that's what we want, right? So you can move them in front, your ds dt. And then what else you have? You have your d theta dx and dt d theta. Let's look at what these dx d theta. So again, your x is theta minus theta naught over beta. If you're doing derivative on both sides, you have dx equals to d theta over beta. Because your theta naught is a constant, so it's gone after one derivative. So in here, it gives us d theta over dx is beta, right? Okay, so what is dt d theta? It's just 1 over d theta dt. So that's 1 over theta dot. So that means we can write it as ds dt times beta times 1 over theta dot. And then by definition, your ds dt is vt. Okay, so that means your Vx equals to beta over theta. Beta over theta dot times Vt. So that's how you convert the boundary conditions in time domain to x domain. All right, so if you don't remember all these chain rule, so you just need to remember these relationship. That's how you deal with your velocity. And then the third one is how to deal with acceleration. So again, we start from the definition. Your AT, your time domain acceleration is just ds dt, second derivative. And then your A in x domain is just ds squared dx. So it's a second derivative with respect to x. So what we can do? So your AT also equals to dvt dt, right? Just single time derivative for velocity. And then we already know that your vt can be written in vx. So that means your d beta over theta dot vx over dt. And then beta over theta dot, that's just a constant. You can move it in front. And then you have dvx dt left. If you have dvx dt, then you can use the chain rule. You can add dx, dx d theta, and dt dt. So it makes sense? So if you recall this x domain thing, so it's also dvx dx, right? Because everything is with respect to x in this domain. So we can find out your dvx dx. That's something we want. So it's going to have beta theta dot times your ax times your dx d theta times d theta dt. And then remember your dt here is gone. and then you're collecting terms following this off diagonal direction. Okay, so again, what is a dx d theta? We already calculated that in previous step. Dx d theta is 1 over beta. Did have something wrong. Oh, I think I had something wrong here. Because we're replacing Vt by Vx. So you have to actually reverse the coefficient. So that's actually theta dot over beta. And then the same thing, that should be theta dot over beta. All right, that's theta dot over beta. And then let's look at here, dx d theta, that's just 1 over beta, and d theta dt, that's just theta dot. Okay, so by merging these, by replacing these terms, you're going to have theta dot over beta square ax equals to at. So if you don't remember, so that's if you cannot remember this chain rule, so that's the relationship you're going to remember. Okay, so if you want, again, if you want to put an ax on the other side, on the left hand side, and then leave all the other on the other side, then you can move things around. Just remember to revert the direction. All right, so that's for acceleration. The fourth question is, how about jerk? Even though we're not assigning any strict constraints on jerk in this case, but then in the future you might also want to control your jerk profile. So how to correlate jx and jt. I'm not gonna go over these again, but you can easily make an assumption, because for velocity is order of 1, acceleration order of 2, then naturally you can guess that in jerk that should be the order of 3. Okay, so that's something you can remember. All right, so up to this point you already know how to convert boundary conditions between t and x domain. So let's go back to here. We already know the theta dot is 2 pi radian per second. We know the beta. And then your st equal to 0 corresponds to sx equal to 0, right? And then again, as we said before, you can directly copy and paste the displacement. And then what is your Vx x equal to 0? So by definition, I'm going to write it in here. I'm going to use your Vx is beta over theta dot times Vt, and then your Ax is beta times theta dot square At. So your beta is 2 pi, your theta dot is, your beta is 1/6 pi, and then your theta dot is 2 pi. So that gives you 1/12 times 0 is still 0. So there's another small trick here. So if your velocity and acceleration there is 0, so that means you can dump this 0 between different domains directly without that relationship. So again, your Ax equal to 1, that's going to be 0. Then your Vx x equal to 1, because when time equal to 1/12 seconds, that's the other side of the segment, so that corresponds to x equal to 1. And then by definition, you're going to have 10 over 12, that's 5/6 if you want to give it. So that's 5/6. All right, so 1, 2, 3, 4 equations. You can plug this back into the 3 polynomial, and then you can solve for C1, C2, and C3. So I'm going to directly give you C1, C0, C1, C2, and C3. So let me see. So your C0 is going to be 0. C1 is also 0. C2 is 5/6. And, oh, sorry. Your C2 is, oh yeah, it's 5/6. And then your C3 is minus 5 over 18. All right, that's your SX for the first one. So you're going to have (5/6) x squared minus 5/18 x cubic. And then because eventually we want to add theta, so just replace x by theta minus theta naught over beta. Then you have a function of theta. So that's something we want to have in the end. All right. So let's look at the second segment. So in your second segment, let's plot whatever we have already. So we know that you have your S, you have S theta, you have your theta V, you have your A theta, and then we know that in this case your theta naught is 1/6 pi, and then we know that your beta is pi, right? And then that means starts from theta naught and it ends at theta naught plus beta. And then we know that in this domain is going to be flat. And then you remember that this is actually in the is actually flat, and then your acceleration is all 0, and then your displacement is gonna be going up. Okay, but then as I said before, we don't know the starting point. But once you, after designing your segment number 1, we actually able to get these boundary conditions, right? So that's from your segment number 1. So let's name it the segment number 1 as S1 theta. So that means this question mark equals to S1 theta when your theta equals to 1/6 pi. Or if you want, you can write it as S1 x equal to 1. If you plug 1 back in, you would note that this displacement is about 5/9. Okay, because we can dump things around in S domain, we can move things around freely in S domain, then it's 9/5 for this point. All right, so this segment 2 is actually special. We already know that it's a linear relationship, and then it starts from 5/9, and then the angle here is our velocity. So your velocity in time domain is 10 meters per second, We want to dump everything in x domain. So in x domain, that's beta over theta dot times your 10 meter per second. Again, you have to make sure, you have to pay attention that your beta here is different. So which means when you focus on one segment, you have to use the beta and theta naught in the same segment. So in here, your beta is pi. Your theta dot is 2 pi times 10. So that's why eventually your velocity in x domain is 5. So that means this tangent theta angle is 5. So that means the slope is 5. And then you know the crossing point. So that theta naught corresponds to x equal to 0. That also corresponds to x equal to 1. So your s for the second domain S2, x is going to be the slope times the crossing point. If you want, you can write it as theta, and then it's going to be 5 times theta minus theta naught over beta, and then plus 5 over 9. So that's your second segment design. Okay, then let's move on to segment number 3. And first of all, let's find out the starting point. Theta naught equals to, which is 7/8 pi. And then we know that the beta is, I think is 1/6 pi again. And then let's plot all the s, VHA, we already know. So starting from theta naught all the way to theta naught plus beta, that's the range of your segment. And then you have your theta, you have your V theta, you have your A theta. Okay, so we already know that the velocity here, that's the end of the previous step, so that's going to be a constant velocity, 10 meters per second. And then it's going to return back to 0. So that's something we already know. So the displacement, the acceleration, it should be 0, because that's starting from the initial, from this previous segment. And then this displacement is a question mark, but this question mark can also be solved. So this question mark equal to S2, x equal to 0, right? X equal to 1. So that's the ending displacement from segment number 2, which means your segment number 3 should directly follow the segment number 2. So that's why we already know you plug x is equal to 1 back into there, and then you have 50 over 9. All right, so this is known, 50 over 9. And then we don't know here. So let's circle out all the known values we have. We know the starting point. We know the velocity here. We know the ending velocity. We know the velocity at the beginning. So 1, 2, 3, 4 unknowns. The same thing. Let's assume your S3x. So this question mark is actually S3, x equal to 0. All right. So S3x should be 1, 2, 3, 4, third order. C0, C1x, C2x squared, C3x cubic. Same thing, you have your V x, x, you have your A x, x equal to C1 plus 2C2x plus 3C3x squared equal to C2 plus 6C3x. So that's all the equations you have, polynomial you have in the x domain. You want to find all the coefficients, but all the boundary conditions are in time domain. Your time domain boundary conditions are, and when your S time start, the starting point equal to 50/9, and then your V T starting point, that's 10 meters per second. Your A time starting point, that's 0. You want to convert everything to S domain, in X domain. The starting point in X domain is X equal to I forget one more thing. Your VT end should be 0 meters per second. So the starting point in X domain is X equal to 0. So you have S X equal to 0. That's directly copy and paste because it's in S domain. And then you have your Vx, that's all Vt, At, and Vt. You have your Vx, x equal to 0. So that's equals to beta over c dot times 10. And then you're going to have your beta here is 1/6 pi, theta dot again is 2 pi radian per second. So you should have 5/6, and then you have your Ax, x equal to 0. As I said, if you have 0 in your A and V values, you just directly copy and paste. Your Vt x equal to 1 that's your Vx. X equal to 1 is also 0. So 1, 2, 3, 4. You have 4 boundary conditions. You plug these back into these three polynomial. You're able to find your C0, C1, C2, and C3. I'm going to give you the solutions directly. Your C0 is 50/9. Your C1 is 5/6. C2 is 0. Your last one is minus 5/18. All right. Then you can find your S3x equals to C0 plus C1x plus C2x squared plus C3x squared. Okay. If you want to get S33 theta, you just replace x by theta minus theta naught over beta. Okay, so that's segment number 3. And then the last segment, number 4. So very tedious but important. You have to follow the same steps. Find all your theta. That's your V theta. You draw your SVAJ diagram, and then you find the starting point, which is 4/3 pi. Your beta is 2/3 pi. So you start from theta 0, you end at 2 pi. In this case, 2 pi is theta naught plus beta. Okay, and then you need to find all the boundary conditions you know. So in this case, all the boundary conditions are already given, because this segment 4 is connecting to segment 3 on the left hand side. It also connects to segment 1 on the right hand side, because that's how your motion repeats. So that's why you're able to get all the boundary conditions from segment 3 and segment 1. So let's look at that. Again, on the east side, you can directly plug in your x. So this value is S3 x equal to 1, and the ending value here, that should be 0, because that's the boundary conditions we have over there. And then the velocity should also be 0, because that's the zero velocity. That's the zero velocity we're getting. And then because it's 0, you can directly dump it back to the you can directly transfer it between different domains or between different segments. So the question is, what is the v theta here? So v theta here is also 0, right? Because that's the ending point from segment 3. Your acceleration at this point, that's to be determined. And then the acceleration here is also to be determined. All right, so first question, we need to find all the accelerations. So when you want to transfer boundary conditions, okay, so let me write it down. When you want to transfer boundary conditions between segments, it's better to do it in time domain, because the time domain, in time domain we can assume the continuity. Okay, so that means we first need to find what's the ending acceleration at time domain, in time domain after segment 3. So we know that your S3x, and then we know that your AX, that's for segment 3, equals to, what is that? 2 is minus 5/3 x. All right. So we know that's the acceleration. So that means the ending acceleration, AX equal to 1, that's in 5/3. Okay. But then we want to convert these acceleration back to time domain. That time domain, that's the ending time. How can we do that? Then you have to go back to the chain rule, your AX and AT. So your AT is actually, let me record, theta dot over beta squared times AX, x equal to 1. Because x equal to 1 means your time, that's the ending time for that segment. And then here, these beta is the beta. So because all the calculations we're doing is in segment number 3. So your beta should also from segment number 3. Your beta should be 1/6. Your theta 2 should be 2 pi square AX. And then let's directly replace your AX by minus 3/3. So eventually that's going to give you a negative value. Let me calculate it out. It should be 144 times 5 over 3 minus. So that's going to give you what a value. So this is going to give you minus 240. Remember, the unit right now is in time domain, so that's meters per square second. So once we know that, we know the ending point in of segment number 3 in acceleration, then we know that these acceleration here should be minus 240 meters per square second. But then again, you need to dump it in back to x domain for segment 4. So segment number 4, you know that your S, you know that your AT T start is minus 240 meters per square second. You want to dump all these back to x domain. You want to calculate ax, and then because t star corresponds to x equal to 0, and then you need to get beta over theta dot square times minus 240. And then recall that here your beta is no longer the beta in segment 3 because the calculation here is done in segment 4. So that's why your beta equals to 2/3 over 2 pi square times 240. So 2/3 that gives you 80 over 3. So that's your new boundary conditions there. So you can do the same thing to find your ax x equal to 1. So your ax x equal to 1, you first need to find the acceleration here in time domain. So that's why you have to start from segment number 1. In segment number 1, so this corresponds to ax x equal to 0. So you're going to have, let's go back to find your ax. In this case, you have to do time derivative twice. That's going to give you 5/3. Let me see. That's going to give you 5/3 minus 5/3 x. And then you have x equals to 1. X equal to 0. That gives you 5/3. And then you have to dump it back to a t, which t is the starting time. And then here you're going to have theta dot over beta square times ax, x equal to 0. And then your theta dot is 2 pi. And then your beta here, because everything is a segment 1, your beta would be 6th pi. Okay? Square times 5/3. That's going to give you positive 240 meters per square second. All right, so that means your ax x equal to 1 equals to beta over theta dot square times positive 240. That's going to give you, oh, sorry, I forgot a negative sign. That's going to give you a 80 over 3 positive. All right, so let me insert one page here. So let's collect all the boundary conditions we have. We have in x domain for segment number 4. So let's go back to segment number 4 again. So you have, oh, we forget one thing. The S3 x equal to 1, what is that? That equals to C naught okay, so let's collect all the boundary conditions we already know for segment number 4. So we know that for segment number 4, S4 x equal to 0, that's 55 over 9. S4 x equal to 1, that's 0. And then Vx equals to 0, that's 0. Vx x equal to 1, also 0. Ax, that's just from previous derivation, 80 over 3. Ax x equal to 1, that's 80 over 3. And then 1, 2, 3, 4, 5, 6 boundary conditions. Then we know that your f4 x should be should have 6 unknowns. That means it's 5th order. And then you can calculate a Vxx from ds4 dx. That's c1 plus 2c2x plus 3 c3x squared 4 c4 plus 5 c5. And then the same thing, ax x equals to 2c2 plus 6c3 plus 12c4 plus 20c5. So that's 3 polynomial. You can plug all these boundary conditions back. Right? Oops. And then you can solve for all the coefficients. Your C naught is 55 over 9. C1 0. C2 is minus 40 over 3. C3 is minus 70 over 9. C4 is 25. The last one is minus 10. And then up to this point, you find all the segments. And then eventually, you have all this S in your for your design. So then you have to write your S theta out. Your S theta out is just S1 theta, S2 theta, S3 theta, S4 theta. And then you express them out. And then that's a piecewise function. So the first one is theta is from 0 to 6 pi. And then the second one is theta from 6 pi to 2/3 pi, I believe. Sorry, I got it wrong. So that should be 7/6 pi. And then the third one is from theta from 7 pi to 4/3 pi. And then last one is from 4/3 pi to 2 pi. And then you remember that in your S theta you have different beta values. So here you also need to mention that this beta is 1/6. This beta is pi. This beta is 1/6. And then this beta is 2/3 pi. All right. So that's the solution for these CAM design.